Hi everyone, it's Mr. Hamilton here. This is the second video on solving trigonometric equations. We're going to solve the three trigonometric equations shown below and discuss some common strategies and some things you want to stay away from that might actually lead you to missing some of the solutions. If you didn't see my first video on that, you can see it in the description below. Let's go solve some trigonometric equations. So here are the strategies that we need to review as we start off part 2 of this lesson. First off, we want to rearrange an equation using the reverse order of operations if possible, so Sam, Deb, bed, miss, in reverse. We want to simplify by isolating a trigonometric ratio if possible. We want to use trigonometric identities to simplify, if we can. We want to factor. Common factoring or using trinomials are the most common ways of doing that. And if we're left with an angle that's 2x, go around the unit circle twice to account for all the angles between 0 and 2 pi. And just a quick review as well, that the x-coordinate of all the coordinates on the unit circle is the cosine of an angle, and the y-coordinate is the sine of the angle. And so that is super helpful to keep in mind when we get our exact answers. Now this problem 4 says find all possible exact solutions for cos squared x minus cos x minus 2. Now we should recognize that looks remarkably similar to y squared minus y minus 2 equals 0. And so we can factor it just as if it was that. And so I want to find two numbers that add to negative 1, multiply to negative 2. Those two numbers are negative 2 and 1. And so now this becomes cos x minus 2 times cos x plus 1 equals 0. It's a simple trinomial because the coefficient is 1, so there's no need to decompose anything. And so now because two numbers multiply together giving me 0 means that one of those two numbers has to be 0. So cos x minus 2 is equal to 0. Or cos x plus 1 is equal to 0. So when cos x is equal to positive 2, and we get cos x is equal to negative 1. Well, cos x represents the x-coordinate on the unit circle. The unit circle has a radius of 1. And so if it is equal to the x-coordinate, you can't possibly have an x-coordinate on a unit circle that's bigger than 1. And so that means that this is not possible. We're always going to get a cos value or a sine value that's less than 1 for the unit circle. And all the ratios always simplify to the same ratios as the coordinates on the unit circle. Now, for cos x is negative 1, well, that occurs at when the x value is equal to the negative of the radius. And so that would be at an angle of pi. And so the only answer here is that we're going to have pi. And then if we go around again, we're going to get 3 pi, and we go around again, we're going to get 5 pi, etc. And so what we can say here is that x is equal to pi plus 2 pi times k, where k is an integer. And so that is our final solution for all possible exact solutions for that factoring situation. So problem 5 says find all possible exact solution on the interval from 0 to 2 pi and all possible exact solutions for cos cubed x over sine x equals cotangent x. The helpful strategy is to use trig identities to simplify. And so what we're going to do is we're going to start by just breaking down the cotangent into cos over sine. So cos cubed x over sine x is equal to cos of x over sine of x. Now at this point it might be tempting to try to cancel some things out, but I'm going to hold on to things as long as possible by factoring, because canceling things out sometimes misses a solution, as I'll show you at the end of this. So what we're going to do is we're going to bring the cos x over sine x to the left side. So I'm going to have cos cubed x over sine x minus cos x over sine x is equal to 0. And because that has a common denominator, I'm going to write this as cos cubed x minus cos of x over sine of x equals 0. And so if I multiply both sides by sine of x, this is going to cancel out. And that's not a problem. So we get 0, and that stays to be 0 on that side. But now I'm going to common factor out a cos of x out of the left. So I'm going to be left with cos squared x minus 1. And what I have here is I have two solutions. I have cos x equals 0, and I have cos squared x minus 1 is equal to 0. Because one of those two numbers, if they're equal to 0 when they multiply, must be 0. So cos of x equals 0, or cos squared x minus 1 equals 0. And so let's go ahead and solve those two situations. If we look at the unit circle, well, when is the cos of x be 0? That's the x-coordinate. The x-coordinate is 0 at an angle of pi over 2, and at an angle of 3 pi over 2. And so that means that x is equal to pi over 2 and 3 pi over 2. Those are two solutions from that first factor. From the other factor, we can take this a couple steps further here. Cos squared x equals positive 1. And then if we take the square root of both sides, that means the cos of x is equal to plus or minus the square root of 1, which is still 1. And so if I draw the unit circle for that situation, where is the x coordinate equal to positive and negative 1? Well, that's going to be at an angle of 0 and an angle of pi. And again, an angle of 2 pi, etc. But we want to stay between 0 and 2 pi. So that means that our angles would also be x equals 0 and pi. And so that would be our solution, those two solutions, if we're trying to go from the interval from 0 to 2 pi. But what about writing an equation for all possible exact solutions for this? Well, you'll notice that every one of these is pi over 2 away from each other, right? If you put those two circles together, we literally had all the angles, every pi over 2 starting at 0. So all of those angles were possible solutions that could exist. So what we could write this as is we could say that x is equal to, well, starting at 0 doesn't really need to be written there, but it's k times pi over 2. So this could be written as x equals k times pi over 2, where k is an integer. And so that is the general solution for all possible exact solutions. Now, I promised you that I would also talk about what a wrong way to do this is. And so here is the wrong thing to do. Do not do this because it will miss out on a situation or one of the solutions. So if instead, when I was at that situation, if I had gone and I divided by cosine of x, if I'd done that, what I would have gotten was I would have gotten cos squared of x, and I could have also multiplied both sides by sine, but I'll do that here in a second. But cos squared of x equals 1 over sine. And so now if you multiply both sides by sine, you get cos squared x equals 1. Well, that's this one right here. That is not the situation on the left. We've completely missed that by canceling that out ahead of time. So don't be dividing things out ahead of time. We want to factor them out so that we can fully see the solution. Factor them out to get all solutions. That is the key. Do not cancel, but factor instead. All right, on to the last problem. Problem 6 says, find all possible exact solutions for cos 2x plus cos 4x equals 0. And so the helpful strategies here are to use trigonometric identities to simplify and to use factoring. So one of the simple ways I can make this simplified as well is I can let y equal 2x. We can do that so long as later on we put that back in. So when I do that, what I'm going to get is I'm going to get cos of y plus cos of 2y equals 0. And we want to use trigonometric identities to simplify this. Well, one of the double angle identities says that cos of 2 times an angle is equal to 2 cos squared of that angle minus 1. And so we're going to substitute that in for cos 2y. So cos of y plus 2 cos squared of y minus 1 is equal to 0. And so now you'll notice I've got a cos squared term, I've got a cos term, and I've got a non-cos term. And so I'm going to write that in order. So starting with the 2 cos squared y plus cos y minus 1 equals 0. And now I can factor that. So just as if I had 2x squared plus x minus 1. So two numbers that add to 1 multiply to negative 2. And those two numbers, we know that factors of 2 are 2 and 1. And the smaller number has to be negative for it to add to a positive. So we get 2 and negative 1. So I'm going to write this as 2 cos squared y plus 2 cos y minus cos y minus 1 equals 0. And now I factor by grouping. I'm going to common factor the first two terms. I can take a 2 cos y out. I'm going to be left with cos y plus 1. And out of the last two terms, I can take a negative 1 out, and I'm left with cos y plus 1. I better have the same thing in those two brackets. And so I get 2 cos y minus 1 times cos y plus 1 is equal to 0. And so now I can solve those two different solutions. So I'm going to look at 2 cos y minus 1 equals 0. Well, that means that 2 cos y equals 1. And that cos of y is equal to 1 over 2. on the other side, cos of y equal plus 1 equals 0 means that cos of y is equal to negative 1. Well, what is cosine? Cosine, if you remember, is the x-coordinate of any point on the unit circle. Well, where do we have that to be a half? Well, the x-coordinate is a half at an angle of pi over 3. It's also a half at an angle of, down here, of 5 pi over 3. Pi over 3 is the related acute angle in each of those two cases, or the angle measured from the x-axis. It's not in quadrant 2 or in quadrant 3 because those would be negative values for the x-coordinate. So it's only in those two. Now, remember here that what we did is we actually let y be 2x. So what we're going to have to do is, because y is 2x, that means that 2x is equal to pi over 3. And so that means that the first angle is pi over 6, and that 2x is equal to 5 pi over 3, which means that x is equal to 5 pi over 6. If we continue that, because we have to go around a second time when we have 2x as the thing we're trying to solve, and so what we get is we get 2x is equal to, if I go around another time, I go 2 pi plus pi over 3, so this is going to be 7 pi over 3. And then if I go all the way around down to 5 pi over 3 after going around once, that's 2 pi plus that. And so that's going to give me a total of 11 pi over 3. And so if I solve those two as well for 2x, so 2x equals 7 pi over 3, that gives me x is equal to 7 pi over 6. You can see that's between 0 and 2 pi. And then 2x is equal to 11 pi over 3. That gives me x is equal to 11 pi over 6. So those are all the solutions that are just from 2 cos y minus 1 equals 0 part of it, the 4 solutions that actually work. We still need to look at this other situation of cos y equals negative 1. So if we do that, if we look at the unit circle there, what we can see is, well, when is the x-coordinate equal to negative 1? The x-coordinate is equal to negative 1 right there when we're at pi. But because we're going around twice, because we're solving when 2x is the angle, so we have to go around to 3 pi as well. So 2x is equal to pi. That gives me x is equal to pi over 2. And 2x is equal to 3 pi, which gives me x is equal to 3 pi over 2. And so those are all the solutions that I have between 0 and 2 pi. Those two, and then the other 4 rather, that I mentioned before. Now, what we need to do is write a general equation. You'll notice that in order to get between any of these, there's no common way to do that. They're adding different things when we're going from the solutions for this one, for example, compared to the solutions for this one. But what is common is that we add pi to get between these two solutions. And we add pi to get between these two solutions. And we add pi to get between these as well. And so when we're writing the general equation, what I can do is I can say x is equal to pi over 6 plus k times pi. X is equal to 5 pi over 6 plus k times pi. And x is equal to pi over 2 plus k times pi, where k rather, is an integer. Where k is an integer. And so that represents all the solutions, all the exact solutions for cos 2x plus cos 4x equals 0. If this has been helpful, please like and subscribe. For more on solving trigonometric equations, you can see the video on the left. On the right, there's a video about proving trigonometric identities. Thanks so much for watching, and hope that was helpful.